About 40 light-years from Earth, 7 worlds orbit a single red dwarf. Could any of them truly host life, or are our hopes just mirages dissolving inside a crimson flare? Welcome to TRAPPIST-1. Tucked in Aquarius, this tiny M-dwarf is about 1/10 the Sun's mass, dim, cool, and magnetically feisty. Around it circle 7 roughly Earth-sized planets, labeled B through H. Pack the whole system into ours, and almost all of those orbits would fit inside Mercury's. That crowding helps lock the system into an elegant rhythm. Several planets are caught in a finely tuned resonance chain, a cosmic metronome ticking in orbital time. Closeness to the star implies something else. Most of these worlds are probably tidally locked. One face basks in unending daylight, the other lies in perpetual night. Between them runs the terminator, a twilight ring where winds may never rest as they shuffle heat from day to night. If a stable, life-friendly zone exists on a locked world, the terminator is a prime candidate, especially if the atmosphere is thick enough to transport warmth, but not so thick that it broils the surface. That brings us to the central question: atmospheres. Red dwarfs may be small and faint, but they're active, throwing off flares, ultraviolet light, and high-energy particles, especially in youth. Such onslaughts can erode upper atmospheres and, in extreme cases, strip them away. A puffy hydrogen-helium primary envelope would trap heat and could turn a small world into a mini Neptune. A thinner secondary atmosphere, built from outgassing and impacts and dominated by nitrogen, carbon dioxide, and water vapor, could yield temperate conditions. Too thick and you bake, too thin and you freeze. Somewhere in between, climates become interesting. Enter the detective, the James Webb Space Telescope. During a transit, a hair-thin slice of starlight filters through a planet's atmosphere, imprinting faint absorption features. Water vapor? Carbon dioxide? Methane? Ozone? Each spectral notch whispers whether air is really there and what it's made of. So far, early JWST transit spectra have not produced strong evidence for big, puffy hydrogen envelopes on the inner planets, an encouraging hint for terrestrial-style climates, while stellar spots and flares keep muddying the signal. Separating what belongs to the star from what belongs to the planet is painstaking work. More transits and complementary measurements will tighten the case. Let's stage a small habitability tournament with 5 criteria. 1. Stellar energy and heat balance. 2. The ability to retain an atmosphere. 3. Tidal heating's pros and cons. 4. Exposure to stellar activity. And 5. Whether a climate can keep liquid water stable somewhere on the surface. Start with TRAPPIST-1e. In terms of energy input, it sits near the system's sweet spot. Tidal locking is likely, but the terminator belt could turn that into an advantage. If surface pressure is at least a meaningful fraction of Earth's, global winds can ferry warmth from day to night and blunt extreme temperature contrasts. Flares remain a risk, yet ease distance softens the worst of the star's tantrums compared with inner neighbors. Bottom line, a strong contender. Move to TRAPPIST-1f. It receives less starlight, so a CO2-rich atmosphere may be needed to avoid a deep freeze. Too much CO2, and you risk global glaciation via condensation at the poles or on the night side. Too little, and you freeze anyway. Tidal heating should be weaker than on E. Less internal stirring, fewer guaranteed volcanic outlets, but also less risk of runaway heating. Bottom line, cautiously optimistic. Now TRAPPIST-1g. It lives near the outer edge of what we call temperate. Sustaining liquid water might demand a thicker atmosphere and stronger greenhouse effect. Theoretically possible, but the same stellar activity and long-term atmospheric escape that threaten the inner worlds could make maintaining that thick blanket harder out here. Bottom line, uncertain, not eliminated. What might life feel like under a red sun? Picture a small habitat perched on a ridge along E's terminator. The sky doesn't bloom blue, it leans toward wine red and coral. The star keeps its ruddy hue even near the horizon. Winds never truly sleep, forever carrying heat from day into night. On the day side, there is no sun-bright white. Photosynthetic life, if it arose, might favor pigments tuned to red and near-infrared photons. On the night side, the air is stiller, the sky pitch dark, and the distant stars prick through with surgical clarity, while a dim crimson halo marks the direction of your star. For all the romance, caution rules. TRAPPIST-1's early UV and particle flux may have thinned or removed atmospheres, particularly for the inner planets. Earth weathered a turbulent youth too, yes, but our star's spectrum and activity cycle were different, and our planet spun freely with a strong, rotation-driven magnetic dynamo. Here the playing field changes. Low visible light, relatively strong infrared, frequent flares of variable intensity, and slow spinning locked worlds where magnetospheres may not look like Earth's. Which observations would most clarify habitability here? 3 golden keys. 1. A secure carbon dioxide detection. Mid-infrared CO2 bands would indicate greenhouse muscles strong enough to warm a cool surface. 2. A credible water vapor hint. Even a modest terminator region signal would point to an active, moist troposphere. 3. Heat redistribution. Thermal phase curves mapping day-night brightness could show whether winds and clouds efficiently shuttle energy around the planet. JWST has begun to prod some of these levers, but crisp answers need more transits, careful treatment of stellar contamination, and different instruments covering complementary wavelengths. Soon, ESA's ARIEL aims to survey exoplanet atmospheres across a broad sample, and next-generation ground telescopes, think extremely large mirrors with ultra-stable spectrographs, will try to prise starlight and planet light apart at higher resolution. That 1-2 punch could move us from, is there an atmosphere, to how much, what mixture, and under what climate. Zoom out, and TRAPPIST-1 becomes less a fantasy of another Earth, and more a laboratory where physics and chemistry stress-test the word habitable. Tidal locking, stellar tantrums, atmospheric escape, these are not disqualifications, they are exam questions. If any world here passes, it won't be a carbon copy of home. It would be something stranger, life under a red sun, thriving along a twilight ring where the wind never stops. If I had to cast a vote today, I'd choose TRAPPIST-1. Balanced energy input, a reasonable chance at holding on to a secondary atmosphere, and a terminator climate that could land in the just right range. But science loves a plot twist. One new spectrum could reshuffle the leaderboard. Stay tuned. The first clear breath of a red sun world might be closer than it looks.